Okay, I'm gonna hide the floating control thing. All right. Okay. So last time we started talking about, or was in the middle of discussion of the angular momentum in quantum mechanics, right? So angular momentum in classical mechanics is just the radial vector cross producted with some particle that has some momentum p, right? And this cross product turns into this, either from just knowing the equation or doing the determinant of this function, right? And in the homework, I'm going to have you guys derive all these commutation relations, because you know the commutation relation between y and pz. Right? What's the commutation relations between y and pz, by the way? Actually, let's start off with the easier one. What's the commutation relation between y and py?
It's I.
It's just I, right? But if they are in a different direction, what is the commutation relation? Yeah. The negative I, if you switch the order of this, right? Because this is just a subtraction operation between them, right? That's actually negative I. But if they're in different direction, the commutation relation is actually 0, right? Because one direction of position and one direction of momentum, they actually do not need to be, they're not correlated to each other, related to each other. Okay. So you can do that, and then hopefully you'll get a bunch of fun. Well, I think I just have you guys derive one and just say, okay, use the cyclet to write down the other ones. Okay. As opposed to having you do 3 different ones. Okay. But the problem is that these angular momentum don't commute with each other. But what happened is that L squared, basically the magnitude square of the angular momentum, does commute with all the directions. And therefore, that gives us a way to write a eigenstate, right? Where we may have some lambda, which is the eigenvalue for L squared. Let's not have this long arrow. Let's just write it, right? The eigenvalue for L squared. And then M, and we'll figure out why these letters are the way they are, right? Is the eigenvalue for the angular momentum in the z direction only, okay? And then we also constructed these, yes?
So is that notation, that's just how you like write eigenvalue?
It's you write the eigenstate. So the eigenvalue could come out at different numbers, right? Depending on what lambda and m's are. Right? Yeah, this is the this thing called the bracket notation for states, right? Okay. This little, because remember where this came from, right? When we calculate the expectation value of x, right? In statistics or something like that, people will write it like this, but then we'll blow it up into like this, right? And now it makes sense for these things to be, represented by these little right alligator things, right? And this is called the ket. If you really want to know, this is called the bra. Probably better name for this is called brackets. Okay. So we also constructed these raising and lowering operator. And I think last time we left off of why they're called raising and lowering operator, because if I skip down to here, right, where we left off, right, if we acted on a state that started off with lambda and m, okay, and we put it into LZ, right, the z direction, right, oops, I point the arrow at the operator instead of the state, right, what happened is that instead of getting m back, you would get m plus 1 back from the LZ operation, right? This operator gives you m plus 1, right? It's as if this raising this L plus operator, right, increases the m value by 1 all the time, okay? And you will see that it's going to be the same thing if you apply the lowering operator. It will lower the m value by 1, okay? But it does not affect lambda, right? Okay, and this is sort of like the nice pictorial view that we didn't get to show you last time, is where, since we're just thinking about angular momentum in the z direction, right? What happened is that you can think about the magnitude of the angular momentum as kind of like, I think we kind of talked about this last time, as kind of having like a sphere, right, shape. on a shell where the radius to that shell is the magnitude of this angular momentum of your whatever particle, atom, or whatever system you're talking about. Okay. And the z direction, right, is like a little projection of that. Right. So this will be LZ. This will be a different LZ. Okay. Okay. And LZ can be negative, right? Because it could go down in this direction, where the magnitude is always going to be positive, right? Okay. And the neat thing is that the L here, right, this factor here, right, has to be always bigger than LZ, right? Well, bigger than or equal to, right? That's the biggest one you can get, okay? Because you cannot get to LZ bigger than this if you're constricted to this sphere, right? Yeah. Okay. And therefore, right, let's say if you have an angular momentum L equals to 2 in this example, right? So the M state, the possible M's, right, you can start off with +2, +1, 0, -1, -2, right? So those are the 5 possible angular momentum state in the z direction, okay? Okay. And then if you have L equals to 3, right, it gets just the list just gets longer, right? Right. You start off with 3, 2, ... to -2, -3, right? So hopefully this pattern makes sense. Okay. I know I jumped into L before we actually derive what L actually is. Okay. So if you actually apply the angular momentum operator square, right, replacing it with this one, go back up, right, replacing it with L minus L plus LZ squared. And once again, I'm going to let you guys do this in the homework because we only get, there's really one problem we're trying to solve here, right? So if I solve all the problems, you don't get any homework. Okay. Okay. And so this L squared just turns into this, 3-term operator. Okay. If you act on this with L minus L plus, then you get a 0. But then LZ will give you, right, whatever the angular momentum is in the z direction. And then, but this LZ squared gives you the L squared instead, okay? And therefore now we can figure out that, well, comparing the two sides of this, right, we can see that lambda is actually, whatever this lambda thing we called before is actually not physical, but it's actually more important to know that lambda is actually equal to L times L plus 1, okay? Right? And this is actually the angular momentum, right, magnitude, okay? Okay, as opposed to where, right, M is the, whatever the angular momentum in the z direction. Let's see, right, right. Hopefully that's illustrated in this picture up here, right, where this length is actually L, and then LZ is the distance up in the z direction. Okay. Okay. Right. So the thing we want to get out of this is that, this is an example where you have 3 operators that does not commute with each other. This is just a really good commutation relation example, okay? We're not trying to deal with angular momentum. Well, we're going to have to know what the angular momentum of different particles is when they interact with each other in the future. But the point of this exercise is so that we know how to deal with commutation relations, okay? We know how to switch these operators, what happens when you switch them, okay? And then also recasting L squared in terms of an LZ, recasting Lx, Ly in terms of L squared and Lz allowed you to have commuting operators, okay? In this case, that shares an eigenstate L and M, right? So if you operate on L squared on some eigenstate L and M, right, the value you get out of here, right, is L plus 1, right, plus the whatever state you had before, right? Okay. Similarly, I know I'm not drawing the operator hats all the time. Sorry about that. Similarly, if you have the same state, right, this will give you whatever this M value is times the original state, right? These are the same eigenstates, right? Okay. And I'm not sure this is actually a lesson we need, it's like the point of this whole thing. But what happened is that you're going to see in the homework, especially, that these L plus and L minus operators like changes the Z value of the Z component of your angular momentum. But then what happened is that if you go from, I think in the homework I have you guys go to basically M equals to negative L, right? And then what happens to that? Okay, and you'll see what happens. And then I'm not going to ruin that fun for you. Okay. And these are combinations of Lx and Ly operator that has the same functionality, right? When we declare them, we don't know what it actually does, right? But when we apply them to the eigenstate, what happens is that it just kind of raises and lowers the M value in our eigenstates, okay? So these are the key lessons we want to get out of these section, okay? It's just a good example of dealing with operators, dealing with commutation relations, and applying them to eigenstates and see what happens, and then just doing a little bit of algebra. Okay, any questions? I think I lost my box, right? How did I get the box back? Maybe click on Zoom. I don't have a keyboard. Okay, there it goes. Okay, there's a bunch of stuff on chat. Maybe I should just leave it down here. Okay. There's a heart on the message. Sorry, I couldn't read the whole thing. Okay, so if there's anything, Alex, if there's anything that I need to address on the chat, let me know.
Yeah, definitely. I'll interrupt you if I feel like it's necessary.
Yeah. So the rest of this class, we're gonna kind of get just kind of an initial view of the Fermi golden rule, which is gonna allow us to calculate transition rate, okay, between and this is a little example, like for example, if you had a electron in an excited state in around some atom, like let's say the n equals to 3, so these n's are just different energy level for the particular electrons, okay, and it de-excites and goes to an n equals to 2 state. What is the rate of that because both n equals to 3 and n equals to 2 are valid states for that electron to, I know this is not really what's happening, right? But like, just think about it as kind of like orbiting, right? This electron's orbiting from the Bohr model, okay? And the book really, starts off with a Schrodinger equation and does perturbation, which is a way for us to doing series expansions into the Hamiltonian in order for us to figure things out. And the whole point of the Fermi golden rule, I think in a lot of the lecture note, I just say FGR, right? This allows us to compute transition rates, okay? Right? Let's write it over here on the side here. Right? Rate from some initial state, maybe I'm going to do this. Let's not do the Barquette notation. Let's just do psi I, okay? To some psi final, right? Okay. Right. And so we're going to talk about this more of I'm just going to do an overview of what Thomson did. He did a full derivation of it. So that was like 3 pages of algebra. I'm not gonna be able to do that, especially in a lecture, right? But definitely read through it. But you don't have to like, oh, I don't know how he got from step, equation 2.61 to 2.62. I mean, let me do 3 pages of math to do that for you. Okay, don't do that, right? Just say, okay, it makes sense that you want to go from, step 1 to step 2, but all those little algebra in between, don't worry about trying to fill those in, okay? The way you're reading that book. Okay, so and I'm going to try to do the same thing where I'm just kind of getting the gist of what's a justification for each of the steps are, and describing what the Fermi golden rule actually tells us, and what do we need to calculate in order to use it And that's going to be all of next week, calculating those two factors, okay? This TFI and density of states, okay? Okay. So when a, electron transition from some initial state, let's say this n equals to 3 state, right? This has some Hamiltonian associated or some energy, right? This has some specific energy state for that particular electron plus the atom system, right? Plus the with the nucleus system, okay, right? So this is some initial Hamiltonian, right? This final part, right, has a different Hamiltonian because right now the system actually has a different energy, right? Okay, so the Hamiltonian is changing with time, not Hamiltonian. Just have a hard time erasing with this pen, right? It's depending on time now, okay? And this is where Thomson actually started off, right? Because usually the Schrodinger equation is I times the wave function, sorry, I times the time derivative of the wave function times the Hamiltonian acting on that wave function, right? But now there's some time dependence on it, right? Okay. So what he broke it up into is that, well, there's a piece that does not depend on time, right? I don't know how to write that. Does not depend on time. And then there's a piece that does depend on time. Okay. And we're doing just the first order approximation of the piece that does depend on time. And that's why he's writing this. Okay. Right. So what we're gonna say is that think about this picture of a hydrogen atom with this electron in the n equals to 3 state, right, transitioning to n equals to 2. And how long does that take, right? So that's what people are interested in, okay? So we're going to denote the n equals to 3 state. I'm going to zoom in a little bit, right? As some initial psi, right, psi I, right? If you like the Barquette notation, this is going to be, well, unfortunately, whether or not you like it, the book that uses it, so we kind of have to stick to it. So, and which is in the Barquette notation, right? It's just the little alligator I with the right to the right. Okay. Where the final state n equals to 2 is denoted by some psi final, right? And then in Barquette notation, it'll be just the same thing, but with an F inside the little alligator clip. Okay. Right. As I said, right, this is actually in the introduction paragraph of this section, it's an optional derivation. Okay. And he broke the wave function into spatial and time components, time piece factors, and actually does the full derivation. So I think it's good for you to follow it, but you don't try to fill in every step, okay? Because that's going to take forever. Okay. And so this is, what he did is actually a very rigorous derivation, basically deriving Fermi's golden rule. Okay. Okay. What we want to do is actually just understand enough so that what are the pieces of it in order for us to use it. And next week, we're going to be able to use it to calculate, for example, decay rate of, some particle or something. If you have some boson with some mass, right? Well, if you have some scalar particle with some mass, can't deal with spins yet. Okay. What is how fast will it decay? And if you shoot, one electron into another, how often would they smash into each other or scatter off each other? Okay. And that's sort of the goal of chapter 3, which is what we're going to be spending a whole week on next week. Okay. Okay. All right. So this is Fermi's golden rule. Okay. This thing is the Greek letter gamma. Okay. And gamma Fi, this is known as the transition rate. Okay. Sorry, this is the transition rate from some initial state to some final state. Okay. How fast are these things? How fast is this atom decaying, going from n equals to 3 to n equals 2, right? Whenever we're in this particular section, just think about that particular example all the time, okay? Right? And there's a 2 pi in front, just because there's a 2 pi sometimes in front of your equations, right? And then there's this thing called the TFI, okay? what the heck is TFI? Okay. TFI is the transition matrix element. Specifically, it's going to be kind of what we did in on Wednesday, where it's kind of like the sandwich. Okay, you have the bar and the ket, but then you stick a operator between the two. Okay, in this case, since we're interested in how the Hamiltonian is changing, right, from one energy state to how the system is changing from one energy state to another, right? The changing part is the Hamiltonian, and therefore is actually the time-dependent part, right? This is the time-dependent part of the Hamiltonian that we stick between the two, okay? Yeah. Because if you don't have this time-dependent part, the atom will just stay as n equals to 3 state forever. Remember when something commutes with the Hamiltonian, right? It's a stationary state. That's the thing we tried to cover yesterday on Wednesday, right? And therefore it doesn't change, right? So we need something that changed, right? Okay. Okay. And Thomson was able to break up the spatial part and the time dependent part by just putting an e minus I e. So the exponential of minus I, the energy times time, right? Where these states, right, has these coefficients in front of it, okay, right, and we're actually sticking these into this computation when we need to, but we're not going to do that yet, okay, right. But the important thing right now, right, is these coefficient CK in front of it, because what these CK what is actually describing is it's the CK square that tells you the probability for that state to be either in its initial state or its final state, okay? So if it's the initial state, right, CI, right, where K equals to I, right, that is initially going to be 1 because we know initially, go up here, right, initially, right, the atom is in this n equals to 3 state, right? Okay, so therefore that's why CK, I need the I, CI at t equal to 0, that's equal to 1. But then, right, the CI, the coefficient that determines our final state, right, at t equals to 1, what should that be equal to? Someone on Zoom maybe? Just to grab people on Zoom. What should the coefficient for the wave function to be in its final state initially be, right, at t equal to 0? Okay, yes, that's correct. Remember, these things are, right, these coefficients square is actually telling you the probability for the things to be in one state versus another, right? So initially, we know it's in this initial state, so the 1 square is 1, right, and 0 square is 0, so therefore the probability of you finding that particular atom in the n equals to 2 state at t equal to 0 is exactly 0 at that point. Good job. Okay. Okay. So that's why I wrote down here. Okay. Okay. So the stuff on the right-hand side, we're going to have to deal with that soon. Don't worry about it for now. The reason I copied and pasted this equation is that, yeah, the probability of finding the system to transition from final state to some initial state is actually, we don't care about CI anymore because we want to figure out what is the probability of us finding the atom in the n equals to 2 state, right, after some time, right? And this time, they use the letter capital T instead, okay? So if you're able to calculate this, right, you have the answer, right? Okay, and this little piece, this TFI thing, we're going to see that these are actually going to be related to the Feynman diagram that we drew in the beginning in chapter 1. Okay, and we're going to figure out how we can actually draw that. But these TFI are not Lorentz invariant, not Li. So we're gonna have to do something to change it into this. You know, unfortunately, I'm not able to type in script, right? This scripty FMFI, where this is the Lorentz invariant version. Okay. Okay, but that's a little detail that we're gonna fix in a little bit. Okay, in the next chapter. Okay. So these TFIs, right, are related to these Feynman diagram stuff that we drew. And we're gonna have to, so each Feynman diagram will have a different TFI, okay? But, right, there's still this thing on the back here, okay? This rho EI. Okay, going back to the atom, just erase all this stuff so I can have a clean picture here, right? If there was no electron here, right, this transition could never happen, right? If the atom was never in n equals to 3 state, there's no transition from 3 to 2, right? If you start off with nothing, you can't give the energy to transition down to 2. Hopefully that makes sense. That's I'm not trying to be creepy quantum mechanics with you guys. That's what it is, right? Okay, right? If I don't have an apple up here, I cannot move it down to n equals to 2, right? Okay, let's just make it a microscopic thing. Hopefully that makes sense, right? I know like some of the stuff in quantum mechanics is counterintuitive, but I'm not trying to do that to you guys, right? Try. Okay. So what this row thing is describing is the density of state, right, at the initial energy. So let's say I have, you know, 1 atom, 2 atoms. Well, let's say I have like, you know, 100 atoms, right, where this the initial state is going to be n equals to 3, right? That means, you know, there's a better chance for me to see something go to the n equals to 2 state. I don't even know, we don't know what that number is. This is a better chance, right? If compared to if I only have 5 atoms, let's say at n equals to 3, right? To transition down to the 10 equals to 3, right? Whatever this number is, right? Let's call this, you know, let's not call it X, right? Well, let's call it X, right? And Y, right? We know that, you know, X is going to be bigger than Y, right? Okay, just trying to be, don't think about quantum mechanics for now, okay? Or special relativity. Just think about numbers, right? Okay, because if you start with more stuff, right, there's a better chance for it to, you will get more at the end, right? Yeah, whatever this, you know, transition rate is, right, going down. Okay. Any questions about that? Okay. This is where I'm just trying to give you guys the physical intuition about these things. We're not trying to, in fact, you probably see in the homework, there's no homework on this at all. Okay. Okay. We're going to be much more rigorous. Well, rigorous enough so that we can actually calculate a couple of things from the next chapter, but that's about, and utilize get some practice utilizing the Fermi golden rule. Okay. So this thing here, right, is called the density of states. Right? Specifically at the initial energy. Right? In this case, the initial energy. Okay. All right. Going back to this funky integral here, right? This little piece here that I told you not to worry about. I just want you to kind of picture, while the book shows a good plot of this, that's what I want to show you guys. Okay. Right? Because these EI stuff, right? EI to the EF minus EI. Sorry, exponential to the I, EF, EI. I know there's multiple E's involved, right? Right. So these are just like sine and cosine waves, right? Right. Right. Remember the Euler equation is that e to the I to the x is just the same thing as cosine to the x plus I to the sine of x. Okay. Right. So what these are representing is just sine and cosine waves. And with this negative sign between them, okay, what's going to happen is that the odd function, meaning the sine function, will multiply together to give you sine square, where the even function, the cosine, right, they multiply together to just give you 0. But so this stuff inside here, you can actually recast it. You don't have to do it. If you substitute in x equals to EF minus EI times T over 2, well, even it's not even natural units because you have to deal with the even put in the H bar. You will see that it's just sine square x divided by x squared. You don't have to do it. But what this function look like is this, right? Okay. And there is a good point of why he's showing you this, okay? So this is a very narrow function around 0, okay? So physically, why is that the case? Why does it peak at 0? Or the function that peaks at 0 makes sense here, okay? Looking at these functions, right? Okay, right? 0, right? If EF is equal to EI, let's say you're transitioning from n equals to 3 to n equals to 3, right? Right? That means you're going to have basically the difference here is almost 0. So therefore, you have the very high probability for that to happen. Okay. Okay. Just get the sense of it. You don't have to do any of the calculations. Okay. All right. And what happened is that, yes.
Just when you get the chance, there's a question in the chat that it might be helpful for everyone to hear. So rather than responding, I thought I'd let you address it. Just to clarify about the density of states.
Okay.
So the question is, okay, can you see it or do you want me to read it?
Yeah, I see it. Okay, yeah, so that's a good question. So this is a interesting nomenclature, you know, in physics in general, because we only have 26 letters. Okay, I guess I erased that. So these n's are not representing number, right? This is representing the energy level of a particular atom. Okay, so there's a probability, you know, there is an n equals to 4 level up here, right? But for now, let's just think of it as unoccupied. There's nothing there. Okay. For this example. Okay. Okay. So we're not going to have the density of state also increase if you are in. So think about the density of state as at n equals to 4 as just being 0. We're just trying to deal with we have some atoms in n equals to 3 initially, right? 100 of them. And then we're just trying to figure out how many of them will transition down to n equals to 2 at some time, you know, a nanosecond or something like that. Okay. Does that make sense, Dustin? Or anyone else? Okay. Let me know if that doesn't make sense though. Okay, because I know this n is not, yeah, all these letters are not well thought out, right? Or there's just so many uses for the 26 plus. How many Greek letters are there? Like 23 or something like that? Yeah, we just don't have enough letters. Yes.
For the for that equation, all that recast into that.
Right. Yeah. So if you want to actually do all this math, you can just substitute in, right, wherever. Well, you divide by 2 over h bar here, and then you substitute an x in here, and you do Euler. The question was that how does this equation get recast into here, right? Right. The question, yeah. So the idea is that you have, well, not the idea. The method is to wherever you see here, you substitute in here, and you do the integral, and then you'll see that it will come out. You substitute in this, whatever you see this, and then change it into x. Okay. In fact, you don't even need to do the h bar. Yeah. Okay. And then when you do that integral, it'll come out as just sine square over x squared. Okay. Okay. Okay, let me read this question. Okay. So I mean to ask if the density of state increases at higher level, since particles would preferably move to the lower one to the higher ones. So the density state for, let's say you have a collection of hydrogen atom, right? Yeah, most of them will be in the n=1 state, okay? But then if you shot a little bit of photon into it, you might excite one of them into the n=2 state, and then maybe enough energy to get it to n=3 state. For this particular analogy, so we're not even going to try to calculate anything out of this hydrogen atom right now, right? Just think about that as a two. I mean, if you don't want to think about it in terms of the hydrogen atom, right? Just think about it as a two-state system where you have some initial energy, some final energy, and the thing is just transitioning up and down here. Okay, you just have two states. Okay. Okay. I'm just trying to make the math that Thompson is doing and apply it to a particular system. That way, hopefully, it sticks to your memory a little bit better. Okay. Okay. So the discussion of the sine square over x square thing, right? So you have this very sharply peak function, right, around 0. That means you are most likely, going to find the atom, right, at its initial state. It's not going to try to transition out. Okay, but you can see that there is some width to this function. In fact, there's some ripples, right, because of the sine square part of it. And what these ripples does is that it gives you some resonant states that you're going to see in the future, okay, where certain energy will be more likely, even though the energy is actually further away from the center. Okay. And this density of state thing, okay, right, this rho EI, okay, when we need to calculate it, what we're going to do is we're going to actually take a derivative, okay, with the. So once again, maybe that's my fault for picking an example with n's in it, because this is the example I put in, right? Where this n, this little lowercase n, okay, represents the number density of a particular state. If you take that derivative with respect to the final energy and evaluate it with the initial energy, you'll be able to calculate this. We're gonna spend like a whole lecture calculating this factor next week, okay? Okay. But the reason I brought this up here is that this n is exactly the same n that we started with when we started this chapter. No, we started this section, right? When we were talking about density of particles current, right? Or actually particle current, and how is that related to the number density of a particular particle going from one place to another, okay? Right? Right. And that's just the number density times the speed of these particles, or the velocity of these particles going around. That gives you the current. Just like if you have, 10 apples and they're moving around at some velocity v and with some density, that kind of tells you what the current is. Okay. So going back to our example, what was the question? Right. Get rid of this. Okay. Right. Going back to our example, just to finish up today. Okay. Since each of these states have a certain energy, or we can call it momentum also in case, okay, because there's some angular momentum of this electron whipping around our nucleus, okay. What we're going to see is that in chapter 3, okay, which is going to be the next week, maybe plus 1 day, okay, we're going to have to figure out that each of these states have a particular energy and a particular momentum. We're going to see how we can constrain this calculation, because right now, right, this TFI, let's go back down here, right, this density of state, right, it could be anything right now. We don't know what this density of state is, right? Okay, and this density of state is going to allow us to figure out if, let's say you have, let's do another example here, right? Let's say you have, right, n=1. Let's say you start off with, let's use the one that's what Dustin just kind of talked about, n=4, right? Let's say you have an atom with an n=3 state, okay? What's the probability of it, transitioning up to n=4, right? Okay, is that even possible? Okay, right? In order for this to be possible, you need to give it some energy, right? You need to add some energy to this, right? So is that energy, is that amount of energy accessible to the system in order for that transition to happen? If it cannot, then basically the density of state at, for that final transition is 0, right? Where it is possible for it to transition to n equals to 2 or n equals to 1 also, right? Okay. So the density of state at the n equals to 3 level is non-zero. And then as these atom transitions down, right, the density of state actually goes down, right? Right. If you started off with 100 atom at n equals to 3, 50 of them transition down to n equals to 2, you only have half the atoms to start with now, right? So this will be some funky integral you're going to have to do, and we're going to see how that goes about, okay? That's what most of next week going to be about, and we're going to do some examples of these TFI, some simple examples of these transition elements in order for us to basically get some numbers here so we can actually, get to something that we can actually calculate and put all the stuff we did in chapter 2 and chapter 3 together and have it make sense so we can actually do some calculations of these things called decay rates and also cross sections. And that's what the next chapter is going to be all about. Okay. That's all I wanted to kind of cover today. But, if we want to start chapter 3, we can do that too. Got 5 minutes. No? Okay. Well, why don't we just talk about where the kind of the goal of next week is going to be, okay? Module 4, okay? So the chapter is called Decay Rates and Cross Sections. So the end goal is to calculate a decay rate or have some general equation to calculate decay rates. And also have a way to calculate these things called cross section, and I'll talk about what cross section actually means. Okay, so we're going to start off with Fermi's golden rule, trying to figure out what these matrix elements. Okay, if you don't like that, just start off with TFI and how do we convert that to MFI? So this is the invariant version. This is the non-invariant version, and we're going to see that just comes out to be a factor of 2e or something. Okay. And then we're going to have to deal with a bunch of integrals over phase space. Phase space just means, kind of think about this as like momentum space. Okay. We're going to be doing a bunch of integrals over momentums, but then we're going to get a lot of help from conservation of momentum. Okay. Okay. And the end goal is to calculate decay rates and cross sections. Okay. All right. Wow. That was nice. I'm going to stop recording.